Hello friends, this is Praveen Chobe. Again, I have brought few more numericals for you on design of three-phase induction motor. In my previous video, I have covered few numericals. That was part 4. This video can be considered as part 4B, where few more numericals on design of induction motor I have covered. So this will be again addition in the number of numericals to be solved on design of three-phase induction motor. So let us start the first numerical of the day. Statement of the numerical goes like 15 kilowatt 400 volt 4 pole 50 hertz 3-phase induction motor is built with a stator bore 25 meter and a core length of 0.16. It means in this problem the value of D and L is given. D is 0.25 meter and L is 0.16. This is already given. Then the specific electric loading AC value is 2300 ampere. Then conductors 23,000 ampere conductors per meter, that is the unit for AC, specific electric loading. Using the data of this machine, determine the core dimension. We need to calculate the core dimension. Then number of stator slots, SS has to be calculated, and number of stator conductors for 11 kilowatt 460 volt. Means this data has to be used, and we are supposed to calculate the stator, the number of stator slots and number of stator conductors for 11 kilowatt 460 volt 6 pole 50 hertz motor. Assume a full load efficiency of 84%, means efficiency to be considered as 0.84, and the power factor is to be considered cos phi is equals to 0.82, power factor to be 0.82 for each machine. The winding factor, one more thing, Kw is given in this problem. Kw is equals to 0.955. See, we need to understand, friends, these are two different problem statements. First is starting from this initial part, 15 kilowatt motor. For that the details are given. The details are given up to this point, means the details related to D, L are given, then voltage V is given, then 15 kilowatt is the value given, 50 hertz is frequency. All these values are given for the first problem, which is our first machine, which is up to this, and the remaining data is dealing with the second machine. How I have understood it is, first is 15 kilowatt machine, other is 11 kilowatt machine. So data for 15 kilowatt machine is given, and by considering that data I need to calculate the things related to 11 kilowatt machine. So let us see how to do that. We'll be starting first of all for 15 kilowatt machine. Again I am starting with the same procedure to calculate the kVA input. First of all, kVA will be given by kilowatt upon efficiency into cos phi. So by using this relation I am putting the values. 15 kilowatt 0.84 is efficiency, 0.82 is power factor. So I have got kVA is equals to 21.8. Then synchronous speed ns is equals to 2 into 50 divided by 4. How is it calculated? ns in rps is equals to 2f by p. So number of poles are 4, f is 15. I have got synchronous speed rps is equals to 50 rps. Next step is C0, that is output coefficient, given by q upon d square L ns. So D and L values are already given. In this problem C0 value is not given, but D and L values are given. So by using those values we are calculating the value of C0 as 21.8 is the value we have calculated for Q. Q divided by D is 0.25, L is 0.16, NS is just now calculated, which is 25. So if I put all those values, we'll get C0 is equals to 87.2. That is the output coefficient. Now C0 is also equals to, this is output equation, C0 is also equals to, we have another relation, C0 is equals to L1 KW BAV AC, right? So in this we can say C0 is known, L1 is constant, KW is given, winding factor which is given, BAV value is not known, AC is known, AC is given in the problem. For 15 kilowatt machine, whatever data is given, that I am using. So if I put all the values which are known, I can calculate the value of BAV, or in other words, I could write C0 is equals to after calculations 241.6 BAV. That's what I got. Now flux density and air gap BAV is equals to, that can be calculated by putting the value of C0 here. If I put the value of C0, I can calculate the value of BAV as 0.36. How we did that? Simply we can say from this equation itself we have calculated the value of BAV as C0 value was already calculated, right? So that comes to be 0.36 Weber per meter square. Then further part is related with the pole pitch tau, which is generally equals to pi d by p, that is pole pitch. Pi is constant, d value is calculated, p is known. So if I put those, I will get tau is equals to what? Pi into d value is 0.25 divided by number of poles are 4. So if I put that, that is equals to 0.196 meter tau. Then again ratio L by tau. L by tau is the ratio which has to be assumed, or not assumed, which has to be calculated here, as both the values L and tau are known. So if I am considering that L is given, tau I have just now calculated. So ratio L by tau, if I calculate, that comes to be 0.815. Then this is the calculation up to this point. Just a minute, friends. Up to this point, all the calculations we have made are the calculations related to 15 kilowatt motor. Why we did this? Because we are going to use this data for 11 kilowatt motor also. Let us see how to do that. Then see, for 11 kilowatt motor, from here we are starting with 11 kilowatt motor. So for 11 kilowatt motor, we have to use the same data for 11 kilowatt motor as it is calculated for 15 kilowatt, because 11 kW and 15 kW, these are the two motors, those are having the rating near to each other. 11 and 15, there is just the difference of 4 kW. So these are these both motors, 11 kW also and 15 kW also, both the motors I am considering them as large motors. These are not the small motors, both are the large motors. Using this data calculated for 15 kW, I need to calculate the things related to 11 kW motor. Okay, so what data I need is, therefore I have considered BAV is equals to 0.36, which I have calculated here for 15 kilowatt. AC was the value already given in the problem for 15 kilowatt. Same value I am considering, same value I am going to consider for 11 kilowatt motor also. Further, L by tau value is calculated for 15 kilowatt, C0 value is calculated for 15 kilowatt, same value I am considering. Okay, the difference is P value for 15 kilowatt motor was 4. Here for 11 kW motor, this value is given in the problem as 6. If you go through the problem statement very quickly, we can identify 6 number of poles for 11 kilowatt motor. So that is why I need to consider that 6. Hence there is change in the calculation. What is that change? Let us see. The change in the calculation comes to be here. NS is equals to 2F by P. This is the formula, right? out of which p value is 6 here. Frequency is no doubt 50. So if I put p value is equals to 6, I will get this as 2 into 50 divided by 6 comes to be 16.17 RPS. Correct? This many RPS I get, right? So if I got this value ns I have calculated, the next thing is to calculate by using the output equation, calculate the value of kVA. That is known to us. kVA is equals to kVA input, generally we are calling it kVA input is equals to kW upon efficiency into cos pi, that is power factor. So if I put all those values, I will get that equals to 11 kilowatt divided by efficiency divided by power factor, that comes to be 16 here after calculating. Then the next thing is calculating the value of d square L. How we have calculated that? That has to be calculated by considering the value of by considering the equation more, or say output equation q is equals to c0 q is equals to c0 d square L ns. So in this equation, from this equation I can say I am calculating the value of d square L, which becomes equals to q divided by c0 ns. So q value is 16 just now calculated, ns is 16.17, and c0 value is 87.2. so by putting those values we'll get the value for d square L, which comes to be 11 into 10 raised to minus 3 meter cube. Then the other part is considering the value for L by D. Now L by D here, the ratio L by D is equals to 0.815 into pi by 6. L by D is equals to 0.815 into pi by 6. How we have written this? Again you need to understand the ratio L by tau for the 15 kilowatt machine was 0.815. Same is the ratio for this machine, 11 kilowatt machine, that we have assumed that L by tau is same. So L by tau value is known. Again tau, which is a pole pitch, equals to pi d by p, right? L by tau, this value is known, L by tau. So this value, by using these two equations, what are the two equations I am going to use? First is L by tau is equals to 0.815, first thing. Second thing I am going to use as tau is equals to pi d by p. Here p is equals to 6, that is known, pi is constant, that is also known. So I can get the value for tau in terms of d here, and then the tau value if I put, I will get the value for d. Finally I can calculate this for solution of d and L. I could get d is equals to 0.30, L is equals to 0.125. I hope you have understood. Apart from that, the number of stator slots, how many slots are to be there, that is calculated. Number of stator slots is equals to pi into d, which is I can say number of stator slots are lies between, we have written pi into d into 10 raised to 3 divided by 25. We have divided it with 25, and then it is further divided with 15. So if we consider these two values, number of stator slots, that those values will be either 37 or 63. Number of stator slots are calculated as either 37 or 63. Which value has to be considered? I will tell you. See, this is something really interesting, friends, and we need to understand this very carefully. The motor, if you consider here, is a 11 kW motor. One motor is 15 kW. Same data we have used for 11 kW, and I told you both these motors are not the small motors. These are not at all the small motors. Means these are big motors. So for big motors, the slot pitch, see slot pitch, which is the distance between two slots, it should not be, or it should be lying between 15 mm to 25 mm. This is important thing and twist in the previous problems and this one. Earlier for the small machines, the range was 10 mm to 15 mm slot pitch range. Here for the big machine, the range is 15 mm to 25 mm. Now see how it affects the slot pitch. Slot pitch, which is generally given by YSS, is equals to pi d divided by number of stator slots, right? From this relation, if I write the formula for SS, that is number of stator slots, is equals to what? Pi d upon slot pitch, which is YSS. Now I know for the big machine, slot pitch YSS should lie between 15 mm to 25 mm. Mm is not SI unit. If I convert it to meter, that becomes mm multiplied by 10 raised to minus 3. Hence, I have got an idea that the number of stator slots, see what I have written, SS, number of stator slots are lying between pi d upon YSS is a slot pitch, which is in mm. That is why we have multiplied it with 10 raised to minus 3. This 10 raised to minus 3 in denominator, when it goes to the numerator, becomes 10 raised to 3 in numerator. So in numerator it becomes 10 raised to 3. And that is how by considering two different values of YSS, one is 15, other is 25, two calculations are made and a conclusion is drawn out of it that the number of stator slots are lying between 37 and 63. This is really important thing. So if you have got the idea that either stator slots can be equals to 37 or it can be 63, then the further calculations can be made as, again we are considering number of slots per pole per phase is equals to 3. From that I could understand, as I have 3 phases, I have 6 poles and I have assumed 3 slots per pole. So this calculations comes to be 54. If it comes 54, that is nothing but value of number of stator slots. Number of stator slots is 54. It means it is lying between 37 and 63. Means my calculations are correct. 54 I have got number of stator slots. How I have got that? By assuming the value of 3 slots per pole per phase. I hope you understood this. 3 slots per pole per phase. Generally we are assuming it 3 slots per pole per phase. If by considering 3 slots per pole per phase, if I would have got this value SS, number of stator slots, less than 37, then I am supposed to change this value of 3 slots per pole per phase. If I got the value greater than 63, then again I am supposed to change the value of slots per pole per phase. And if by considering 3 slots per pole per phase, if I got number of stator slots is equals to 54, which is lying between the two values 37 and 63, which I have calculated here, then I could say my calculations are correct and the data which I have assumed, that is 3 slots per pole per phase, is correct. So here for this problem 54 is correct. Then calculating phi m. Phi m can be calculated as 0.36 into pi into 0.3 into 0.125. Now see, all these values are known to us. Divide by 6 again taken. What is this? 0.36, 0.3, 0.125. All those things you will understand from the problem also, or from the given data also. See, if I go through it quickly, I could find from this problem. See, if I go through the data which is available with me, I have been knowing the value BAV is 0.36 Weber per meter square. So BAV, if I consider that value, I could say BAV is equals to generally phi m upon pi dl. This is the formula for specific magnetic loading. So from that, if I am calculating phi m value, I could get phi m is equals to BAV into pi dl. BAV is 0.36, pi value is as it is, 0.3 is the value of D, just now we have calculated, 0.125 is value of L. So putting all those values, and as it is flux per pole, we have divided this calculation with number of poles, that is 6. Hence we have got phi m is equals to 7.07 into 10 raised to minus 3 Webers. Further, delta connection is used here, as star delta connection is used. For delta connection, we are considering the voltage, phase voltage VPH is equals to line voltage for delta connection. This is the relation. Hence, whatever voltage is given in the problem, that is 460 volt voltage for 11 kilowatt motor, that I am considering same as a phase voltage. So that is stator voltage per phase, that is 460 volt. The number of turns are calculated from the output equation, from the EMF equation. EMF equation of 3-phase induction motor, number of turns are calculated as ES divided by 4.44 into F into 7.07. Just now we have calculated the value, that is the value of flux per pole, that is phi m. Further, 0.955 is the another value which is given in the problem, that is we need to understand it is 0.955 is winding factor kW, right? So hence TS is 307 we have got. Total these are the stator turns per phase. Hence total number of stator conductors. Again we know, if I got the value of turns 307 turns, each turn has 2 conductors and there are 3 phases. So this multiplication comes to be 1842. 1842 is total number of stator conductors. How I have calculated? From turns per phase. Turns per phase multiplied by phase multiplied by 2 conductors per turn. That is coming to be 1842. Now if I got total number of stator conductors as 1842, then conductors per slot is calculated by 1842 are total conductors divided by there are 54 slots that we have calculated. So per slot we will get 34.1 conductor. We need to understand there is nothing like 34.1 conductor. 0.1 conductor is not there in existence. Hence we are considering this as 34 conductors per slot. So if we have 34 conductors and 54 slots total, then multiplication of these two will get 1836. Multiplication if we do, we'll get this as 1836. Actually we have calculated this as 1842, but it comes to be 1836. This difference is due to that 0.1 conductor, right? So using 34 conductors per slot, total conductors are 1836, and stator turns per phase, number of turns per phase will be again 1836. See, if you see what is this 1836 is total conductors. So total conductors, if you are converting them to turns, you need to divide them with 2 because each turn has 2 conductors, and per phase, that is why you need to divide it with 3. So that comes to be 306, right? Instead of 307, it is the correct value is 306. And that's how the problem is solved. This is the complete solution of the problem. Then one more numerical we have, which is again a simple numerical. 11 kilowatt 3 phase 6450 hertz and 220 volt star connected induction motor has 24 stator slots, each containing 9 conductors. Calculate the value of bar and end ring current. The number of rotor bars is 64. Machine has efficiency of 0.86 and power factor of 0.85. The rotor MMF may be assumed as 85% of stator MMF, which generally we are assuming. Also find bar and end ring sections if current density is 5 ampere per mm square. So data is given, sufficient data is given in this problem, and this is not the problem on the main dimensions, but this is the problem on the calculation of rotor bar or rotor bar and end rings current related problem. So let us start it very quickly. First of all, stator current per phase is given by 11 into 1000. What is this 11 into 1000? In the given data we will understand. 11 kilowatt is the value given. So that 11 kilowatt is converted to watt. Generally we are writing kilowatt is equals to what? Vi cos phi, right? This should be in kilovolt. So or in other words, this should be simply watt. Power in watt is equals to Vi cos phi. If you multiply it with 1000, it becomes kilowatt. So from this, if I want to calculate the value of current, that is given by simply kW divided by V into cos phi into 1000 moreover, right? So by that I could say, as it is 3 phase, root 3 will again come. So stator current per phase is equals to 11 kilowatt, 11 into 1000 divided by root 3 into, this is 220 is value of V, 0.86 and 0.85. These are the values, those are given in the problem. What is that? 0.86 is efficiency and 0.85 is power factor, cos pi. So if you consider all those, this formula becomes here is 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 equals to kW, means kilowatt, upon root 3 V into efficiency into cos pi. This is the formula, right? So this formula must be remembered, and by this formula we have calculated the current, which is stator current per phase. Then if I got it as 40, further number of stator conductors. In the problem statement it is given as there are 54. The data given as induction motor has 54 stator slots, each containing 9 conductors. So 9 conductors per slot multiplied by 54 slots, that is going to give me the value of total number of conductors, which is 54 into 9 becomes 486. Then stator turns per phase. If I got 486 conductors, this 486 conductors divided by 2, because each turn is made up of 2 conductors, multiplied by 3, as there are 3 phases. So stator turns per phase becomes 486 divided by 6, which is 81. Then stator MMF. Stator MMF is given by 3 into Is into Ts. What is this Is? Is current, stator current. Ts is number of turns. So 3 into Is into Ts, because this is 3 phase current, number of turns per phase, and as there are 3 phases, we need to understand Is is stator current per phase, Ts is number of turns per phase, and there are 3 phases. That is why ampere turns. MMF means ampere turn. So ampere turn when we are calculating, that becomes 3 into I is current, T stands for turns, S for stator. So ISTS, which becomes 9720 ampere turns. Further, rotor MMF. If I got stator MMF, there is relation which is given that we need to consider rotor MMF. Rotor MMF is equals to 85% of stator MMF. So stator MMF is just now calculated, 0.85 of which means 85% of which is the rotor MMF. So that is calculated by multiplying with 0.85, that I have got 8250 ampere turns. Right. Further, the formula for rotor MMF is, but the rotor MMF is SR IB upon 2. SR is number of rotor slots, IB is current of rotor bars. Hence, I can say just now the value which is calculated for rotor MMF, that is equals to SRIB upon 2. So that becomes equals to, or if we equate it, you will get, because see we have calculated the things such as SR. What is that? SR is number of rotor slots. If I look at the problem statement, I will get number of rotor bars is equals to 64. In the problem it is given number of rotor bars is equals to 64. So 64 by 2 becomes, see the relation is SR IB divided by 2, out of which SR is 64. So 64 by 2 becomes 32. So it becomes 32 IB, right? 32 IB is equals to 8250. That's the relation. Or from that we could say IB is equals to 258 amperes. If we got this value IB, then end ring current, which is generally represented with IE, end ring current is given by SR IB divided by pi p. So SR value is known, IB is known, divided by pi p. If we do, it becomes 883 amperes. Area, when we are calculating, that is given by, area has to be calculated by considering the current density of 5 ampere per mm square. So current density generally represented with del is equals to what? Current I upon area. So area becomes equals to I upon del. I upon del. So that is why AB is equals to, area of each bar is equals to AB 258. 258 was the value of current which is calculated. Current of rotor bars divided by 5. 5 is current density. So that becomes 51.6 mm square, and area of each end ring, which is AE, area of end ring, is equals to current of end ring, that is 883 divided by 5 is the current density. So that becomes 176.6 mm. 176.6 mm. I hope you understood this. So with this we stop here today. I hope these numericals will be useful for you and you have found them interesting, you have understood it. If you have any queries related to this, any problems related to this, or something which you have not understood, please post it to me through your comments. I will answer your comments. I will try to address the problems you are facing. Thank you very much. I request you to please like this video and please subscribe to this channel for further updates on design of electrical machines.